Welcome to NOAA Central Library's online platform for the presentation of research and ideas in support of the National Oceanic and Atmospheric Administration's mission. Today's library seminar is titled Introducing CASAL2 for Assessments. The presentation is part of the National Stock Assessment Science Seminar Series, which is developed by NOAA Fisheries and organized by Kristen Blackheart from the Office of Science and Technology. Today's speaker, Dr. Ian Doonan, will be introduced by Kristen. But before I hand over the mic, here are just a few housekeeping items for our live audience members to improve the webinar experience. If you're having trouble with the audio or visual components of GoToWebinar, I suggest that you log out and rejoin us. This resets the software and usually resolves most technical issues. The presentation is being recorded and will be available on the YouTube channel for NOAA Central Library later today. I've added the channel's link to the chat box. Our speakers has shared his handouts, so please feel free to download them from the handouts menu in the webinar control panel. And last but not least, we encourage you to ask questions. So ask them throughout the seminar, even though the speaker will not address them until the end of his presentation. All audience members are muted, so type your questions or comments in the chat box under questions located in the control panel on the right side of your screen. So that last detail, I'm going to hand the mic over to Kristen. Thank you so much.
Thank you, Lisa, and thank you, Ian, so much for being with us today. Dr. Doonan and his colleagues at the National Institute of Water and Atmosphere Research in New Zealand have been really important collaborators for us at NOAA Fisheries as we move forward with developing our next generation software for stock assessment. And there's been a huge amount of interest in hearing about the work that they've been doing on CASAL2. So I'm really excited to introduce Dr. Doonan and have him with us today. Ian has a really interesting background, having completed a PhD in quantum chemistry before moving over to fisheries. So he's got a really broad background on the quantitative side of fisheries, including survey design, statistical consulting, and stock assessments on various deep water species, including the famous orange roughy. Now he really focuses on the fisheries software development, including CASAL2, which we'll be hearing about today. So with that, I'm not going to take up any more time, and I'll hand it over to you, Ian. Thank you again for being with us.
Thank you. Okay, so this is about CASAL2, which is our new generation stock assessment package. The topics I'll be covering will be the fishery context for New Zealand, a little bit about CASAL, and then I'll go on to CASAL2, and then I'll introduce an example assessment, which happens to be hake, and then I'll show you how to run CASAL2 from R, and then I'll go over some input file syntax, and then finally we'll have a look at some example input file segments for hake 1, just to give you an idea of how the input file is constructed. So this is just to let you know that CASAL development has ceased. It still works, but it does use a 2000 error assessment model, so you can still use it, but we're not developing it anymore. So CASAL2 is our version of the next generation integrated assessment. It includes newer assessment ideas, it's more maintainable, and it's easier to expand. So the New Zealand fisheries context, our management is based on biomass targets and limits, so B current as a percentage of B0. And for example, a common soft limit is 20% B0. It's not common in New Zealand to use the Baranoff catch equation. We tend to use the exploitation rate, and because of that, Baranoff hasn't been included in CASAL2 yet, although it is planned to do so. We also focus on Bayesian analysis, so we use MPDs are used to select final runs for management, but the final runs are always done as Monte Carlo runs. And so consequently, random effects are not really needed, and so they haven't been implemented yet, but again, they have been planned. And finally, our management is based on 5-year projections using the MCMC parameter vectors, and sometimes they go out to 10 years. So CASAL, this was our generalized software package, implements structured discrete time-step population dynamics, so it's an integrated assessment. It has self-documented input files, so if you know what you're doing, you can just read the files and understand it. This was conceived in 1999 and the first version was available in 2001. So it's been extensively used since then. That's over 21 years. Why CASAL? Well, we had, at the time, they had design objectives. So we wanted a flexible, generalized statistical age and length structured model. We wanted to assist scientists, so we wanted a standard validated code base with a common knowledge pool of problems and solutions, and we want a standardized interface that self-documents each model. And we also wanted to assist stakeholders in working group meetings, so we wanted a standardized terminology, standardized mathematical descriptions contained in one place, and consistent outputs which allow easy comparisons between models over times and over stocks. And so CASAL replaced, at the time, various individuals had their own programs, which usually were not that well tested. So the population dynamics for CASAL, it has sex, maturity, area, and stock structure options. It has a flexible time period, an annual cycle, and some additional optional population processes. So it can have multiple fleets and fisheries, and they can occur in single or multiple areas. You had two catch equations, Baronoff or exploitation rate. There was alternative forms of age length relationships, selectivities and ogive definitions, and you could also have migrations. So for the estimation and observations, you have to specify the data for the observations, plus the likelihoods and penalties. The data specs had to be set, so you could have abundance or biomass indices, age and length compositions, tagging, migration and maturation data can be fitted, and age and length data can be fitted for growth within the model. And then lastly, you have to specify the parameters to estimate, their bounds and their priors. And you also had to specify what outputs you wanted to get, so you wanted to get fits to observations or the SSB over model years. And there's also an option for a pseudo observation, so you could pull out expectations from some population slice. For instance, you may want the age composition of the SSB over the fishery history, even though you only had 1 or 2 years with data. And lastly, you had to be able to do projections. So has CASAL been useful? Well, yes, it has. It's assisted us in having a standard approach, got consistent results. There's a transfer of scientist skills between stocks and assessments. It allows more efficient use of time, which is important in the New Zealand context. It's helped reduce errors, so it's aided in bug detection and also standardized output interpretation. And it's also allowed us to be more efficient and flexible. So it's allowed faster comparison of alternative model assumptions. And it's also given us a lower barrier to entry. So we have biologists doing stock assessments. They don't need to know all the mathematical details, but they just need to understand the fishery. But there are problems with CASAL. Some problems don't fit the model paradigm. For instance, time varying parameters are limited to the A50 in selectivities. Rich and large models with lots of observations can be unwieldy and too slow to be useful. It's slow and difficult to use as an operating model for a simulation model experiment. And it's also slow and difficult to use as a management strategy evaluation tool. And then some ideas about parameter uncertainty and variability and how they change over time cannot be implemented within the current framework. So basically, CASAL has hardwired fisheries concepts, and they were fixed to what was common in 2000. Why not just modify CASAL. Unfortunately, it's not the best code architecture design, so the underlying code is ugly, so it's difficult for experienced scientists to check what's happening, difficult to modify. Modern methods for code validation are difficult to implement. It has a 32-bit minimizer and code implemented in some places, and it doesn't interface easily with other software. However, the drivers for developing CASAL still exist, so this is where CASAL2 comes in. So CASAL2 design objectives, what we wanted an up-to-date flexible age or length structured stock assessment tool. Unfortunately, the length-based has still not been achieved. That'll probably come in the next couple of years. We wanted it to be easy to learn, to use, and be able to adapt it to new assessments. And it should also encapsulate best practice in its methods and allow for the production of standard outputs for management and reporting purposes. That hasn't been achieved yet, and it needs to be fully documented, and that's almost achieved, although the manual still needs a bit of work on it. So the code objectives, we wanted to make it an open source architecture. We wanted to allow it for different types of use, play nice with Python or R or other software, and it had to be easily extended. So it is written in C++. And then the constraints on the build, we have to replicate most of the current CASAL assessments, obviously, and it must not block any future or unforeseen model structure in the future. Must be self-validating and include modern code design elements, so self-contained third-party code and build environments, integrated unit tests, and build validation tests. And it must be usable for management strategy evaluation simulation studies. And another design choice we did make was we used no or very few defaults. So all model and observations characterizations have to be specified, as well as what outputs to report. So one of the key concepts for CASAL is what's called the partition, which is a word that seems to be only used in New Zealand or maybe Australia. So that's the numbers at age by population strata. So the partition can be thought of as a matrix of population splits, which are rows, and ages, which are columns. If it's a length-based assessment, then obviously the columns are length bins. And for CASAL, these strata are hardwired. So you've got sex, area, mature, and stock. So some strata can have 1 or 2 levels or factors, others are fixed. So sex has 2. You have to have male and female if you have sex in the model. Area can have a specified number, and so for this example, we've got 2. So if we have 2 categories, sex, which is male and female, and area, spawning and feeding, then we have 4 rows. So we've got male spawning, female spawning, male feeding, and female feeding. And so this structure was retained in CASAL2, but we made it generic. So for CASAL2 has no hardwired knowledge of what population categories represent. Their meaning is user-defined by the processes that are specified to operate on them. So any population split can be conceptualized in the CASAL2 partition. For instance, you could have species. But to have meaning, there must be processes to operate on them. Otherwise, a function has to be coded for it, documented, and tested. So species can use currently available CASAL2 processes, so you can have species in, and that has been done. But if you wanted to simultaneously catch 2 species in the same fishery, you would have to write new code. So the population concepts for CASAL2, it includes all the usual suspects, got aging, mortality, recruitment, maturity, and maturation. Obviously, you have to, these are generic and you impose what it means onto the partition. So now you can have multi-species and multi-sex options. So you can have unsexed as a sex level. We want to add interdependent processes. So we want to be able to do density-dependent growth, mortality, etc. We need to add time-varying parameters, which is something we really missed in CASAL. And we have to add parameter transformations to enable better convergence properties. And it also allows for all the usual observations and likelihoods, so which includes tagging. So the current state of CASAL2, all the CASAL model validations and comparisons have been done. So we built 6 test assessments and adapted them to test most of the CASAL features. So they're a little bit, these test assessments are not genuine assessments. They've been fiddled around with, so we can test all the features of CASAL, and it's come through very well now, although we did have problems. We've added unit tests, and we've also got these system tests, which are in total 14 models, which test specific groups of CASAL2 functionality. And currently, I have to let you know that only the Bevan and Holt is the only stock recruitment relationship in the model so far. So here's a comparison with CASAL and CASAL2, and you can see over on the right here, the black and the grey line is the CASAL results, and then there's all these other results with CASAL2 using beta diff or ADOL-C with flags, various flags on. So to do comparisons properly with CASAL, there are some flags in CASAL2 that do exactly the same calculation as done in CASAL. So here's the example assessment that we're going to have a look at. It's the hake 1 stock. The purpose of this is one of the test cases, and its purpose was to test snooty growth and nuisance Q catchability. I've put the directory in here for this test case, so you can download it yourself if you want to have a look at it. And it's based on Matt Dunn's stock assessment in 2018. It's only based on Matt's work. It's not exactly the same. So over here on the right, this is the hake 1 area, so it's the Sub-Antarctic. And the biology for hake has a maximum age of 25 years. Its maximum length is 100 centimeters for males and 120 for females. They mature between ages 6 to 8. They used to have a von Lamphey growth model, but investigators thought that it underestimates ages of large fish, and so they switched to a snooty model, which is one of the few assessments in New Zealand that uses snooty growth. And M has been set to 0.19, and that was done by expert opinion. And we have catches starting in 1975 going through to 2018. So here's the catch. The catch really ramped up in the early 90s and then held for a while and then decreased. So here's some other factors that you have to consider for this particular species. So it's quite common to assume that 100% of mature fish spawn, unless you've got data otherwise. It's a 50-50 male-female split for recruits. There's an 8% aging error for the age frequencies, and the maximum exploitation rate is 70%, which is a common thing to do in New Zealand assessments. And then we have year class strength starting from 1974 to 2016. And the first year in the model is 1975, but you need a year class strength for the year before to get recruits as age 1 in 1975. So the data, there's observer data from the commercial fleet. There's the catch per unit effort abundance series, which is up here, which has wide error bars. And then there's a trawl survey from 1992 on the Tangaroa, and you can see that the error bars make it, there's almost no signal in the survey biomass. So in this particular assessment, there's a total of 51 parameters estimated. This virgin biomass is 43 year class strengths, couple of catchabilities, 2 parameters for the fishery ogive, 2 more for the survey ogive, and they also estimated catch PNF at process error. In the actual assessment itself, they also estimated M, but that's not done in this particular version. So here's a directory structure for this assessment. So over here, I've got this file called run_assessment, and it has a directory for data, figures, models, source, and tables. Here's my .r data, and this Casal2 new exec is the version of Casal2 I'm going to use to run on this assessment. So this is a typical setup for assessments. Try and keep everything separate. Yes, it pays to be well organized, otherwise you run into a mess. So to run a Casal2 assessment, you have a default input file. It's called config.csl2, and all the supporting files have to be in the same directory. So you can see over here, I'll just bring it up. So this is the config.csl2. You don't actually have to have a config.csl2. You can actually specify any file, but this one's a default one. So it's easy to do that. So this file here just has include files in it. So the first one is include population.csl2. So you stream this file, and the only restriction is that it must encounter an @model command first. That's the only restriction on the input files. And then you have an estimation, which is just another file telling Casal2 what to estimate. And then there's the observations, and lastly there's what reports to push out. So all those files are in this directory that's over here. So to run the model, usually I run it from a command box format. So it'd be Casal2-E for estimation, greater than into an out.txt, which is where the results end up, and then a 2 greater than into an error.txt. So all the errors and warnings will end up in a file called error.txt. And in this case here, I'm assuming the default is config.csl2. If you didn't have that file, you have to add this -c in file name into the command line. And in R, we've got this function, run Casal2, which generates this command and runs it via R's system2, which is the way of running Windows commands. The source for that is in this run assessment source Casal2 functions directory. I've zipped up this run assessment, and at the end of the talk, I show where you can pick that up if you want to repeat the analyses done here. So the other run modes that you have is -R, so you run the model once with the initial parameter values. -M, which is you do an MCMC on it. -P to do projection. The other helpful switch is -I file. So this uses the initial values from this file to start the run. And there's about, who knows, 10, 12 other switches. So there's quite a few switches. To get the switches, you just go Casal2-H and you'll get a couple of screens full of switches that you can use. So to run it from R, I've got scripts are in the run assessment /source, and there's 3 files. The first one is just a setup, and over here it creates this dir, which is for directories. So it has $models, so it gives what the model directory structure is. Same with data, figures, tables, and the assessment code. So this helps later on for when you're running models. You just need to change dir, and then you can just repeat all the code. So this is the first one. You run the hake assessment. First thing we do is we source in the run Casal2 code, and that's made by combining the dir $assessment code and run casal2.r. And then we put the input directory as hake. So hake exists under model. So this is where the command files are held, and then this model joins them together, and that gives the path name. And then you just execute this R command here, and this is, I'm going to use that casal2 new.exec to do the run. And when you execute that command, you end up getting this output here, and it also outputs the actual command that it's sent to Windows. So this is the command that was sent. So let's have a look at a couple of the files that would have been generated. So here's the error file. So it's e.er.txt, and this is the start up here. So it gives you a warning that some of the parameters had upper and lower bounds were equal. That means they're not being estimated. And then it tells you all about these reports that it's generated. And then if we go to the end of the file, you see this convergence check. This is just a way of checking to see how far it's got through. If you do it in a command box, then this will come up on the screen. And then it gives you a couple of warnings showing that a couple of parameters are on the lower bound. So this is the E out text where the output comes, and these are all organized in things called result blocks. They all start with a star, and they have this name here, square brackets, and another name here, and they finish at star n. So this enables our extract function to take these blocks and build a list. So at the top of this file, it has the call that was used, the date, and the user and the machine. And then this is the first output. So this is a thing called star initialization partition in it, gives the values, and this is the star n is the end of that. So this is the male and female, and this is the age, this is category 1. So that just gives you the partition. When you're initially setting up these models, it's quite good to have a look at these things, make sure it's doing what you think it is. Further down, we have a summary, estimate summary output block, and it has all these things here, and it's got a list here, list and end list, because there's a number of parameters that have been estimated. So this long name here, this is the way you specify B0. So it's a process, square brackets, the name of that process, which happens to be recruitment, the closing bracket dot B0. And then you get all this stuff here. And then right at the end of that summary, here's the last one. You've got a star n at the end of that block, and you've got a list, n list. And so this is for the year class values for 2016, which is the last one. And so this name here, this is the way you identify elements within a vector. You use this curly bracket notation. And then after that, here's the objective functions, and it gives the objective function by each year and data type. And so we have an R function that adds them up over this name here, which I'll show later. And so here's the results, which is the third file. And so the first thing you have to do is you have to get the Casal2 library involved. We have to bring in this obj.r, source it, because that's what's going to add up the log likelihood. So this should really be in the Casal2 package. And here's the results file. And then we use a Casal2 extract.mpd results file. And so this Cas2 MPD is a list which here's some of the names of it. So have catch-rent effort down here. That's the fit to the catch-rent effort, and all these other results. And then if you want to plot the SSB, you use the R library's plot derived quantities, and we say plot is false because we're going to use this code here to plot it. And then in addition to that, we'll do a plot fit for the tan biomass in December. And then down here, this split objective function is a way of adding them all up over data. So here's what it looks like. So here's all of the objective functions down here and the total down here. So these ones are data. These top ones are data. From B0 down, they are priors. So here's the SSB. So you can see it has a real peak right at the start and then just slowly declines. And this is the fit to the catch-rent effort. So you can see it's sort of okay, but it's not the best. So now I'm just going to go over some example syntax of the input files, and after that I'll go through a couple of relevant blocks for hake 1 just to show you the flavor of input files. So for the input file specification, we've got a series of command blocks. Each block specifies some aspect of the model structure or processes or data, and these always start with an @ So @ marks the start of a command block. And then when you get a new @ for the next block, that marks the end of the preceding block. So there is no @ end, if you like. So this is the structure. You have a command and a label followed by type and a type. So here's a couple of examples. So you've got an @ selectivity. It's got a label sub-AF cell. It's a logistic selectivity, and it's followed by the initial values for the logistic parameters. So that's A50, A to 95, and alpha, which is the cap. Sorry. And here's another one with @ observation. Again, it's got this name, label, and it's of type biomass. So in the input file, you can use white space freely. You can include another file from anywhere just by using the include statement in the file name. These included files are always placed in line, so you can continue a block in another file. And these blocks are actually organized into a hierarchical tree structure. So you have @ model as the top level block. Therefore, that's why you have to encounter it first, although includes don't count. So here's some more command blocks, and you've got the @ model at the start, and we're specifying the time steps. We've got 2 time steps, July, January, and February, and June, and these are just labels. They have no meaning in CASAL at all. And so this July, January, CASAL expects an @ time step with the same name, July, June, to occur. And then here's the processes subcommand, and we ordered them. We got aging, recruitment, and fishing. And so this aging, recruitment, and fishing, again, these are just labels, and it expects to find another block later on labeled aging, another one labeled recruitment, and another one labeled fishing. And then just showing the one for aging. So here's at process, aging, the type, it's aging. And so this just tells Casal2 to call a function which just shifts numbers along a row, which is the age axis. And here's the categories, which I'll cover later. Star, which is a wild card. So that means all rows of the partition. And so here's
Ian,
some. Yep.
Ian, sorry to interrupt. Just want to let you know, 20 minutes to go.
Okay, thanks very much. So here's some keywords. There's the at, there's this comma, which separates components in the list. So you might have male, comma female. Star is a wild card. Colon, which is a range. So you can say 1951 colon 2010. Plus is a join operator. So you could say male plus female. So that usually it's an observation. So it means the observation is for the combined sex, not for males and females separately. Comments start with a hash, or if you want to enclose multi-line comments, you go hash star and star slash, and type is another reserved word. So here's some segments for the hake1 model. So the first thing you want to do is scope the model, use the at model command. So here it is over here. So we've got the minimum age is 1, maximum age is 30, got a plus group true, time steps July, January, February, start year is 1975, the final year is 1918, and this is the initialization phase. So this is a way to get the initial age structure. You specify that, and then in the next one we've got at categories, and this is another important command. So format, in this case, is only one category, sex, and the names we've given it as male and female. Although, as I said, you don't have to say it's male and female. You could say X1 and X2, but obviously it's better to make them descriptive. And then after that, you have to specify the growth for males and a label for growth for females. And then here's the initialization phase. Again, it's got this same name that was up here, and the type is derived. And then you have to define processes and their use. So here's one for the at time step. We've already gone over this one. So we have the first time step is aging, recruitment, and fishing. And the next time step just has fishing. So there are 2 time steps with fishing in both of them. So here's recruitment. So it's at process. The label is recruitment. So it has Casal2 doesn't know that it's recruitment, but does know the type is recruitment, Bevan and Holt. So now it knows what the stock recruitment relationship is. It works on the categories of males and females, or you could have used a star for both of them. And this proportions tells Casal2 that it's a 50-50 male-female split for new recruits. B0 is the initial value is 60,000 tonnes. The year class strength values is 1, it is 44 of them. So this is a way of writing out 1 star 44 will give you 44 of them. The year class strength years start in 1974, go to 2017. Got a steepness of 0.8. And this is the SSB. You need, this is capital SSB is just a label, and there'll be another block further down telling you how to calculate the SSB for the Bevan and Holt recruitment. And then lastly, this is standardized the year class strength years. So this is being standardized over 1974 to 2013. So they are, the mean of that is set to 1. The fishing process is quite long, so I've split it into two. So this is a process, and it's called fishing. That label is fishing. The type is mortality instantaneous. So this means we can have both fishing and natural mortality at the same time. So we have set M to be 0.19, and it operates on all the characters. I'll just skip some of those other ones. And now we have another important concept. It's called a table. Its keyword is table and catches, and the next line has year, and this is Sub-AF is the name of the fishery. If you had two fisheries, you'd have Sub-AF here, and then you'd have another column here headed by whatever the other fishery name is. So we have years down here and catches down there, and this makes it readable. In CASAL, these years would all be on one line, followed by all the catches would be on one line, and it's very hard to line them up, and you can't read it very well. And then this is the end of the table here at the top bit, and then there's another table called methods, and you can see on the first row there's some labels. So it's got the method, and the method happens to be on the next line Sub-AF. The categories happens to be all categories. You use the star. The selectivity is the Sub-AF cell, and so on. And then there's a penalty, and this is fisheries catch must be taken. There's a penalty that's specified somewhere else, and so if you can't take all the catch, you invoke this penalty, and then you have an end table to finish it. And I think this is getting towards the end. So the next thing you need to specify is at estimate blocks. So you need to estimate some parameters. The parameter names have this command, square bracket, label, open bracket, dot, and the parameter name. So we've got an at estimate. Here's a label. This is just a label. The parameter is selectivity in a block called supra F, and it's A50. This type is just the prior, so that it's got a uniform prior. The lower bound is 1 and the upper bound is 25. And again, this is for the same selectivity, but you have to have a separate block for each parameter. So this is for the A to 95. And again, the type is uniform, and the lower bound is 0.1 and the upper bound is 50. And I think that's just about the end. So this is the license that operates under. The funding was from Ministry of Fisheries and NIWA. Where you can find the source code installations is given here, which is open, public. The active development team consists of Scott Grammerson, who's our architect, software architect. There's Teresa, Alistair, Stephen, Craig, and myself. And the code that I used here can be found in this zip file, and also the actual release that Casal2 knew is in this version here. And that's it. Thank you.
Excellent. Thank you so much, Ian. That leaves us about 10 minutes for questions, and I hope that all of you will ask them by entering them in the questions chat box, which is in the control panel. And before we start addressing these questions, I just wanted to thank one of our audience members who gave the link to CASAL2, which I have put in the chat, and also remind you that Ian has shared his slides with us. So if you're interested in seeing some of the presentation he just showed us, you can go ahead and download it from the handouts menu on the right side. I'll start with a compliment, Ian. Somebody in the audience says, fun talk to hear, thanks. And he asks, any comments about back-end processing?
Sorry, any
comments about back-end processing?
It's probably, what does he mean by that? Is that being able to run it from R?
Hopefully he'll respond in just a moment.
Yep.
He says making figures, etc.
Oh, you use the R library, the R Casal2 library.
For reports, he says.
Yeah, yeah. So you read it in using the extract function, and then there are some functions that will do plots for you, and then you cut and paste them into your report.
Excellent. He thanks you for the response. Let's give this another second to see if we get any more questions. And also just as a reminder that we have been recording this, so I hope that if you know anyone who would be interested in learning more about CASAL2, that you will go to the NOAA YouTube channel later today and share the link to the presentation with any colleagues who might be interested in hearing more about this. All right, give it another moment. Here's another question. This question asks, how many selectivity options are available roughly?
5 to 10. So we have double normal, all values bounded, logistic cat. There's even a double exponential thing that was needed for one assessment. So about half the ones that were used in CASAL have been carried over. So the ones that haven't been used that much, there's a tendency not to install them.
Excellent. Another question asks, do you have any insight or comparisons about run speed compared to CASAL?
Yes, it's now apparently faster. It used to be slower, and then Scott did some work on it, so it now runs quite a bit faster for one particular assessment. I think it's the hake assessment. So yeah, that was one of the goals, was to speed it up.
Excellent. Another question asks, are parameters estimated in phases or all at once? Is there possibilities for controlling this?
Yes, there is. There's a command in the estimate block. You can put phase, and then you can say one is the first phase, 2 will be done second, 3 will be done third. So you can control it in that sense.
Wonderful. Another question just came in, and it says, thank you, Ian. Do you have any advice for us on testing code during the development phase? Also, does CASAL2 run forecasts?
Forecasts, that's called projections, and that's a standard stock assessment practice. And then for testing code, I would imagine you would take some of your stock synthesis 3 assessments and check them out in detail. That's the best way of doing it. If you're putting in new features, then you have to do quite a bit of extra work to generate simulated data so that you can check it. And then of course you have simulation error, so you have to be careful. You have to use thousands of runs to get it as close as to the expected value as possible.
Excellent. That appears to potentially be our last question. I'll give the audience just one more moment before we wrap up. But meanwhile, I wanted to just thank you for joining us today on this webinar, and to especially thank you, since I believe it's fairly early in New Zealand right now.
It's 10 o'clock in the morning,
Oh,
so
okay.
after this I'll go for morning tea. So it's not that early.
Oh. Yeah, my calculations are completely off. Well, I think that's it then. Again, thank you so much. And Kristen, also thank you for organizing the National Stock Assessment Science Series. Audience, I am so glad you joined us for today's seminar. NOAA Central Library is very proud to present the work of the NOAA community. It's its partners like Ian, and we hope you will join us again for a National Stock Assessment Science Seminar, which we host the first Thursday of every month at 3 p.m. Eastern Standard Time. Again, I encourage you to share the recording that I will have uploaded to NOAA Central Library's YouTube channel in about 2 hours, and enjoy the rest of your day. We just got a message that says, thanks, Ian. Happy New Year.
Okay, thank you.
All right. Have a wonderful day, everybody. Take care.